Fascinating. Well, enough of that. This is a video where you're going to learn how to take derivatives and integrals without actually knowing any calculus. Meaning, you're just going to learn how to procedurally go about it. So if I give you a formula for something, and you recognize, I'm supposed to take a derivative of that, you can do it, even if you don't actually know how to do any of the calculus that would allow you to know how to do it. Okay, so to start with, thing one is you need formulas for these things. So, the derivative formula. There's only one that you are going to have to know for this class. And that is for taking the derivatives of functions that are called power functions, which are anything that look like this. So in other words, it's like a constant times a variable to the some other constant. So for example, 3t squared, or 4t to the fifth. We will even look at some ones that are like 2t squared minus 6t. Okay, and those you take the derivative of the exact same way. All right, what the derivative for a power function works out to always is going to be an t to the n minus 1. The meaning of this is basically that you will take a, the constant that's out front, times the old exponent, and the new exponent for your variable is your original exponent minus 1. So as you can see then, if we take the derivative of something like 3t squared, a is 3, n is 2, so an is 3 times 2, which is 6. And the new exponent is 1 less than the original, and so therefore the derivative of 3t squared is 6t. You can get quite good at this after just a very small amount of practice. So I'll do one more, then I'll do this one, and then if you like, you can make up any number of examples you like for yourself and go ahead and do them. So 4t to the fifth. an is going to be 20, and the new exponent is going to be 1 less than the original. So the derivative of 4t to the fifth is 20t to the fourth. If you have something with multiple terms in it and you want to take the derivative, you just simply take the derivative of each individual term, and as long as they all follow this format, then they all come out the same kind of way. So if I took the derivative of 2t squared, the derivative of this term would be 2 times 2 is 4, and the new exponent is 2 minus 1 is 1. And then for this one, this one might sometimes perhaps give you pause. Like, I don't know, what do I do there? What's the exponent, if it's not written, is of course 1. So we would have minus 6 times 1. T to the 1 minus 1 is 0. All right, so that means that one doesn't have a t in it because t to the 0 is, of course, just 1. So all things considered, the derivative of 2t squared minus 6t is 4t minus 6. All right, let me change the problem ever so slightly, because you will also see it where it's like, and plus 15. Remember that a derivative is a slope. It's a rate of change. The rate of change of a constant is 0. So if I take the derivative of just the number 15, since it's a constant, that will just be 0. So any constant terms always have a derivative of 0. That actually does fit with this formula, because you could think about 15 as being the same as 15t to the 0. So therefore, an would just be 0. And then you wouldn't have to worry about the rest of it because it doesn't matter what the new power is for t. Okay, so there we are. That's taking derivatives. All right, now, integrals are antiderivatives, and this is a useful context to say that, right? The fact that derivatives are an integral is an antiderivative means that the formula for the integral of a power function really just undoes exactly this. All right, so here's your integral formula. The integral of something that looks like a t to the n is a over n plus 1 times t to the n plus 1. So it's the opposite of what we did over here. Over here we did, all right, coefficient times the old exponent, and the new exponent is 1 less than the original. When you're integrating, you do the exact opposite of that. You divide by the new exponent, and the new exponent is 1 larger than the original. Okay, so using these same examples then, if I said I want to take the integral of, actually let's do this, let's take the integral of 6t. All right, all this stuff here is just notation, at least as far as you're concerned for this class. All right, this is the thing we're taking the integral for. This says we're taking the integral with respect to time, meaning time is the variable. That's the extent to which you probably need to care about that. Using my formula here, a is 6. The exponent right now is 1. The new exponent then would be 1 plus 1 is 2. So we'll divide by that new exponent, and there's the, okay. So 6 over 2 is 3, and 1 plus 1 is 2, so 3t squared is the integral of 6t. So if we come back over here, we said the derivative of 3t squared is 6t. The integral of 6t is 3t squared. Integration and derivation undo each other is what that is showing you. Okay, same story here. If I do 20t to the 4th, and I take the integral of that, I would get 20 over the new exponent, and the new exponent is 1 larger than the original, so we get 4t to the 5th, which is what we knew it ought to be, since the derivative of 4t to the 5th is 20t to the 4th. Okay. The same kind of thing is going to happen if you want to take the integral of something that has multiple terms in it, is you just take the integral of each individual term. Okay. I should mention at this point, since the calculus teachers would object if I don't, actually, when you take an integral, there's always a plus some constant that you get. For physics class, that is going to correspond to an initial value. So, for example, if your integral tells you the position of something, then the constant here at the end would be the initial position. So if you have an object that starts at the origin, then that would mean that the constant of integration would just be 0. If it starts at the origin, the initial position is 0, and therefore this number here would be 0. Okay, so let's take a specific example more closely related to physics. If they said that the velocity is 3t plus 4. If they said, find the position function, given that that's the velocity function, you would have to know whether you're taking an integral or a derivative. That'd be the first step. All right, if you're not sure, then you'd look back at your notes and you'd say, my notes say position is the integral of velocity. This is the velocity function, so if I want position, I'm going to take the integral of that, because that's what I do. Now, the integral of something like that follows this formula up here. It has two terms, but that's not a problem. We take the integral of each term separately. 3t is going to work like our 6t that we took the integral of up here, right? This is t to the first power. So when I take the integral of this term, I'm going to have 3 is my a, 1 is my n. So there's my 3 over n plus 1 right there. And then t to the 1 plus 1 is 2. And that would be the integral of the first term. All right, now the second term, if you're integrating 4 and you're like, it's a constant, so it's 0. Nope, that's not how it works with integration. That's how it works with derivatives. If you're taking the integral of a constant, the integral is not 0. Let's use this same kind of trick that we did over here, though, to establish how that works. If it's the number 4, then it's really, if we like, 4t to the 0. Using our integration formula, then, if I take the integral of 4, we would get 4 over n plus 1 would be 0 plus 1, which is 1. And then the new exponent would be no longer 0, but 1. So the integral of 3t plus 4 would be 3 halves t squared plus 4t. So that means that my position function, if that's my velocity function, is 3 halves t squared plus 4t plus whatever the initial position of the object is, which is probably going to be 0 most of the time, at least for this class. There we are. Okay, if you did feel like you didn't fully grasp that, I invite you to rewind the video, go back to some point where you feel like you got confused, watch it over again, look at the examples again, make sure you're figuring them out right. If that's still not working for you, come see me in the morning and I will be more than happy to help you. All right, thanks for watching.